Good afternoon everyone, and welcome to today's worked exam answer video. Today I'm having a look at an AQA A-level question which uses calculations and knowledge of group 2 compounds, which both are taught in the AS component. So those of you in year 12, if you haven't already done group 2, will be doing it at some point this year. And then you will be able to answer this question, and year 13 students, you should already be able to answer this question using the knowledge that you gained last year. So it's a bit of a wordy one, and it's one that takes quite a bit of thinking, and I know I've certainly looked at this question before and dived in and used a mass in the wrong way because I haven't thought carefully about what that mass was of. So hopefully I'll be able to break it down and everybody will be happy on exactly how I've arrived at my answer. But as always guys, please feel free to leave a comment on the video or drop me an email, okay? So we're first of all given a powder, and the powder is going to have its own colour, and this powder is a mixture of two different things. So the powder is a mixture of anhydrous barium chloride. The anhydrous just means without water, and the other substance in there is anhydrous magnesium chloride, and again that just means that there's no waters of crystallization, so we can work out those formulas like we always would, using the charges on the barium ion as Ba2+ and each chloride ion Cl-. So we've got barium chloride BaCl2, and the magnesium chloride will be MgCl2. So we've got a white, it doesn't say white, we've got a powder containing those two substances. We are dissolving 1.056 grams of the powder into water in a conical flask, and we are adding an excess of sulfuric acid. This is where our group 2 knowledge is going to come in, because we need to appreciate how different group 2 sulfates are more soluble or less soluble than others. So we need to know the trend in solubility of the group 2 sulfates, which we'll come back to in a minute. We're then told that a white precipitate was formed. So from the original powder, which is a mix of those two group 2 compounds, we are making a white powder, a white precipitate, sorry, from that powder. That was formed, filtered off, washed and dried, and the mass of the white precipitate was measured at 0.764 grams. So we have to identify what the white precipitate is and calculate the percentage by mass of the magnesium chloride in the powder at the beginning. So when it comes to thinking about the masses, the mass that we've been given is the mass of the white precipitate product. So we first of all got to work out what that product is, use that to work out which of the two group 2 compounds formed that white precipitate, to then be able to think about mole ratios and masses and so on. So first thing is identifying this white precipitate. So when magnesium chloride and barium chloride react with sulfuric acid, we're going to make magnesium sulfate and we're going to make barium sulfate. So those are our two options here for the products of that reaction. HCl will then be the other product. So what we are thinking about is the solubility of magnesium sulfate compared to barium sulfate. And what we need to know for our group 2 sulfates and hydroxides is that there is a trend as we go down the group in each of them, and the trends are opposite each other. So as we go down group 2, the sulfate solubility decreases. So magnesium sulfate is the most soluble, because we tend to only think about these 4 group 2 elements in these sorts of questions. So magnesium sulfate will be the most soluble of the 4, and then they'll get less soluble, and then we'll get to barium sulfate, and that will be the least soluble of all of them. The hydroxide trend is the other way round. So the barium hydroxide is the most soluble and magnesium hydroxide is the least soluble. And one of the things we need to know about barium sulfate from our group 2 topic is that because it is insoluble, we can give patients requiring x-rays a barium meal, and once that's been digested into the stomach and the intestines, they then get their x-ray, and the barium helps those organs show up better on the x-ray. And even though barium ions are toxic, we can give people a barium meal because things like the barium sulfate are completely insoluble. So it's not going to get into the bloodstream, it's not going to cause any damage. The patient will then pass it out of their system without it doing anything else. So that's a really important fact that we need to know. And that's the first thing that this question is relying on us knowing. So we can identify the white precipitate. And when it says identify, we can identify it by name or by formula. It hasn't said name the white precipitate, it hasn't said give the formula of the white precipitate, so we can do either. So barium sulfate, which is BaSO4. I wouldn't recommend doing both. I've done both so that you know kind of that you can do either one or the other, because if you did both and let's say you made a mistake with the formula of barium sulfate, you then lose the mark for the name. So I feel like the names are a safer bet if you're not 100% confident with the formulae and you can identify, so you can use the name. But we are going to need the formula because we're going to need to write a balanced chemical equation, which is the other reason why I've written down the formula here. So to work out the percentage by mass of magnesium chloride in the powder in the beginning, we're going to have to use the mass of the white precipitate we've made, which is the barium sulfate. We can then work out the moles of that to work backwards to get the moles of the barium chloride. Then we can get the mass of the barium chloride and thus figure out how much of the powder mass is left, and that must be then the magnesium chloride. So let's give that a go. So first of all, my balanced chemical equation. So barium chloride BaCl2 plus H2SO4 will make BaSO4 plus HCl, and we're going to need 2 HCl because we've got the H2 from the SO4 and the 2 Cls from the barium chloride. So what we now know is that the mass of the white precipitate, 0.764 grams. So I can then make myself a mass MR moles ratio, little table. The ratio comes from the balanced chemical equation, which between the barium chloride and the barium sulfate is 1:1. So as soon as I've worked out the moles of the barium sulfate, the moles of the barium chloride we had in the beginning will be the same. So first of all, I need to work out the MR of barium sulfate. The relative atomic mass of barium, 137.3, not one you're likely to be familiar with. Sulfur 32.1, 4 lots of 16 for oxygen, gets me an MR of 233.4. And then moles is mass divided by MR, so 0.764 divided by 233.4 is going to give me the number of moles. So I'll put a little divide line in there. And mole-wise, that gives me 3.27 times 10 to the minus 3, to 3 significant figures. Now I'm going to leave that whole calculator display value on there. But if you were to then use your answer to 3 significant figures, you will still get an answer that falls in the range that you are allowed. So either or is fine. If you are going to use the whole calculator display, do write to 3 significant figures or whatever number of significant figures is required, as opposed to the whole calculator display on the piece of paper. And please don't write things as fractions, but then you can leave the whole calculator display on, which is exactly what I've done. So that means then that my moles of barium chloride is going to be the same, 3.27 times 10 to the minus 3. And then I need to work out the MR of barium chloride, so the 137.3 for the barium and 2 lots of 35.5, which gives me an MR of 208.3. And then mass equals moles times MR, so if we times those together, we will then get our mass for the barium chloride, which I got to be 0.682 grams. And again, I've written that to 3 significant figures. Now, what some students might have done here, and what I believe I've done in the past, is use the mass of the white precipitate solid as the mass of the barium chloride, not the mass of the barium sulfate, and failed to then get the moles of the barium sulfate and compare product and reactant in terms of moles to then get the mass of the reactant, which was the barium chloride, because the powder in the beginning was a mixture of the barium chloride and the magnesium chloride, and we're trying to get the percentage by mass of the magnesium chloride in the powder, not the mass of the magnesium sulfate solution that was made after the reaction with the sulfuric acid. So now we know that, and we know the mass of all the powder is 1.056 grams, we can then do the 1.056 take away the 0.682, and that should give us the mass of the magnesium chloride, which comes to, again, I've left the whole mass of the barium chloride on there and done 1.056 minus answer, and that has given me 0.374, and again I will go for 3 significant figures here. So that's now the mass of the magnesium chloride. Now, to get the percentage by mass of the magnesium chloride in the powder, we're going to need to do the mass of the magnesium chloride divided by the mass of the powder times by 100. So 0.374 divided by 1.056 grams times 100. And that gives me a percentage by mass of the magnesium chloride of 35.4%. And again, I've gone with 3 significant figures for my final answer, because if we look back to the values we were given in the question, we had the mass of the white precipitate as 0.764. That's 3 significant figures. Yes, the mass of the white powder was to 4 significant figures, 1.056, but we always give answers to the lowest number of significant figures that were used in the values provided to us. We cannot be more precise than our least precise value. So 3 significant figures here to match the 3 significant figures of that mass value there. And that, guys, is our final answer. So just to recap, key things here: we need to know the trend in solubilities of the group 2 sulfates, specifically to answer this question, but also the trend in the group 2 hydroxides in terms of their solubility as well. So once we knew that it was barium sulfate that was going to be the white precipitate, we could then use the mass to get the moles of that white solid made, use that to get the moles and then the mass of the barium chloride in the original mixture. We knew the mass of the mixture, so as soon as we knew the mass of the powder, we could then take away the mass of the barium chloride. So I'm just going to add in there that that is the powder, that is the barium chloride, and that then told us how much of that mixture of powder was magnesium chloride. Then for the percentage by mass, mass of the magnesium chloride divided by the mass of the overall powder times 100, answer to 3 significant figures, because that's the lowest precision in the question. Hopefully that's been clear and understood, but as I said, any questions, please do let me know. Thank you so much for watching, guys. Any requests, please do hit me up as well. Thanks so much.